Hello everyone, welcome to a new lecture on machine learning. Today we will dive into the fascinating world of artificial neural networks, or neural networks in short. This topic is the bedrock of modern artificial intelligence and deep learning. We are going to explore not just what these networks are, but how they learn, how they are structured, and the sophisticated mathematical mechanisms that allow them to perform sophisticated computations. Think of it as the session where we open the black box of AI. So here we go. Here is a roadmap for our discussion today. We will start with the fundamentals, like what is an artificial neural network and how does it compare to the biological brain. Then we will cover the essential component, specifically the activation function. This activation function introduces nonlinearity into our models. The core of our lecture will be based on learning in artificial neural networks. In here, we will study two main algorithms. The first one is forward propagation algorithm. This algorithm is used to calculate the output. Then we will apply backpropagation algorithm, which is used to teach the network. Finally, we will wrap up by discussing hyperparameters. Hyperparameters are the tuning knobs of our network. And then we will study some optimization techniques that are used to help them to learn faster and better. There are mainly two types of neural network. One is a biological model and another one is artificial model. Human brain is densely interconnected network of neurons. They are connected to each other, and we want to make this network in computer as artificial models. So in artificial models, we want to have many neurons like threshold switching units and many weighted interconnection among units to have a highly parallel and distributed processing system. So artificial neural network is an interconnected group of nodes, and we inspire by simplification of neurons in brain. We call it as biological neural network. So our main goal is to mimic human brain. Human brain computes in an entirely different way from conventional digital computers. The brain is highly complex, nonlinear, and parallel. At the same time, we can think of many things in parallel. Organization of neurons to perform tasks much faster than computers. Typical time taken in visual recognition is approximately 100 to 200 milliseconds. So there are some key features for biological brain, that is, experience in biological brain shape the wiring through plasticity, and hence learning becomes the central issue in neural networks. To truly appreciate the design of artificial neural networks, first we must look at its inspiration, that is, human brain. The brain is an incredibly complex, as I said, nonlinear, and also it's a parallel system. Consider these staggering statistics. Here we have 10 in power of 10 neurons in human brain, and each neuron can connect up to 10 in power of 4 to 10 in power of 5 other neurons. It's too many, right? This is a massive and it's a very huge interconnected communication system. What's even more fascinating is the difference in speed. While a single neuron switching time is 0.001 second, the brain can recognize a complex scene in about 0.1 seconds. This is possible because the brain executes massive parallel computation. It does not use a few fast processors. Brain uses countless slow, parallel, and our goal with artificial neural network is to mimic this distributed and parallel processing capability. Let's zoom in the biological neuron, which is the basic unit of brain. A biological neuron fundamentally performs four actions using dendrites, soma, axon, and axon terminal. As you can see here, dendrite, soma, axon, and axon terminal. A biological neuron receives input from other neurons through structures that we call it as the dendrites. Then a neuron merges and processes this input in the main cell body that is called as soma here. And then a neuron performs an operation, for example, deciding whether to fire an electrical signal or not, which travels down to the axon. Then a neuron outputs the result, that is a signal, and this will be done through a axon terminal here. So this will be connected to dendrite of other neurons. This simple input processing output mechanism is what we abstract, and we simplified it into our artificial models. We want to make artificial neural networks based on this structure. The artificial neural network is built upon this biological principle that we have seen. We define an artificial neural network as a massively parallel distributed processor made up of simple processing units or neurons. Each unit, or we call them as artificial neuron, has a natural property for storing experimental knowledge and making it available for use. Artificial neural networks resemble the brain into two key ways. So the first one is the knowledge is acquired from the environment, how through a learning process, not explicitly programmed like traditional computer systems. And also, knowledge is stored in the connection strength between neurons, which we call them as weights. This means the knowledge is distributed across the entire network, making it robust and fault tolerant. The learning is performed by adjusting learning algorithms, weights, topology, and etc. that we will study later. Artificial neural networks are inspired by the biological neural networks that constitute human brains. Artificial neural networks learn to perform tasks by considering examples, or you can say data. So in here, we are not going to program them explicitly with any task-specific rules. Artificial neural network is based on a collection of connected nodes, or you can say artificial neurons. Artificial neurons are analogous to a biological brain. Each connection can transmit a signal from one artificial neuron to another, like synapses in biological brain. So an artificial neuron that receives a signal can process it and then signal additional artificial neurons connected to it. So here you can see we have an artificial neural network here. This is made of some layers. You can see here. The first one is input layer. The last one is output layer. And in between, we may have one, two, or more hidden layers. So we will study them later one by one. So we can define artificial neural network as an information processing system. Artificial neural network was essentially developed as a generalization of mathematical modes of human cognition. Information processing occurs at many neurons. Neurons are connected to each other using some links or channels. Each link is associated with some weight, and the output is determined by applying an activation function on its input by the neurons. Again, we should know that the artificial neural network is to imitate the human brain. So this is our main goal in artificial neural network. We have a corresponding element in artificial neural network as it is in the brain. So let's map biology to code. Dendrites, weights. Soma, input function, or you can say summation function. Axon, activation function or transfer function. Axon terminals, output. So we are not going to copy the brain. We are inspired by the brain. How artificial neural network works. Each neuron receives its input via a connection to the neurons in the previous layer. Each link is associated with weight. Therefore, the input is multiplied by its weight. There is also threshold. We call it as the bias. Bias is used to produce some useful output as desired. The modified input is then sent to a summation function, simply sum up the products. The output of the summation function is then sent to a transfer function or activation function. For example, you can go for a sigmoid function or step function. The output is either sent to the neurons in the next layer or even to an outside connection. There are mainly two types of artificial neural network. The first one is single-layer neural network and multi-layer neural network. Single-layer neural network, this is also called as perceptron. So the single-layer perceptron is the foundational example of artificial neural networks. This one consists only of one input layer and one output layer. We don't have any hidden layers here. Its core use is for a simple linear classification. While historically significant, its severe limitation is that it can only separate data that is linearly separable. It cannot solve non-linear problem like the XOR problem. On the other hand, we have multi-layer neural network, or you can say feed-forward network. This overcomes the limitation of the single-layer perceptron. How? By including one or more hidden layers. So each hidden layer learns increasingly abstract representation of the input data. For example, in image recognition, the first hidden layer might detect basic ifs. Then we have another layer, and this layer might combine these into shapes. Then we may have some other layer that assemble these into complex objects. So with a sufficient number of neurons and nonlinear activation function, multi-layer neural network can theoretically approximate any continuous function. This makes it very powerful for solving complex and nonlinear machine learning problems. So in summary, artificial neural network takes in data, train itself to recognize patterns, and then predicts the output. It's not like fuzzy logic that needs rules. There is no rules here. Just examples plus math is equal to intelligence. So what are examples? Data set that we need. Data. It's a kind of supervised learning. We need to have data and labels. So examples or data plus math is equal to intelligence. In order to build an artificial neural network, we need to know these keywords. The first one is batch. So here, you remember I said we need data or example. Suppose we have 10,000 images, right? We cannot give all the images at one time. So a subset of data. So a subset of data is called as batch. For example, we divide this one by 50 and each one is 200, right? So 200 images in one batch. Then we have iteration. Whenever we have one forward plus one backward on a batch, Then we call it as one iteration. What is forward, what is backward, we will study later, right? So when we have one forward and one backward on each batch, then we call it as one iteration, right? So if we have 10,000 and our batch size is 200, then we need to have 50 iterations. Then we may have some error. The error value is the amount by which the value output by the network is different from the target value. For example, if we require the network to output 0 and it give us 1, the error will be simply -1. Then we have epochs. One iteration over the entire data set is called as epoch. So presentation of the entire training set to the neural network is called as epoch. It means one full pass through the entire data set. We usually train for tens or hundreds of epochs. Then we go for validation set. We use a validation set to select the best configuration. For example, to select the best number of epochs, stop training when the validation set error increases. For example, we want to know how many epochs do we need, right? So from here, it's decreasing, right? And then suddenly here decreases. So if we go to this number of epochs, we will face the problem of overfitting. If we go for less than this number, then we will face the problem of underfitting. So here is the optimal number of epochs. So here we see the architecture of the neural networks. We have input layer, we have hidden layers, we have activation function, weights, bias, and output layer. The input layer introduces input values into the network. There is no activation function or other processing here, just we feed raw data to our network. Then we have hidden layers. We may have 1, 2, 3. So these are the hidden layers. So this input layer, hidden layers, and this is the output layer. So we may have 1, 2, 3, or too many hidden layers. Hidden layers perform classification of features, or you can say feature extraction. 2 hidden layers are sufficient to solve most of the problems, and features imply more layers may be better. Then we have activation function. The activation function defines the output of that node, give an input or set of inputs. Then we have weights. Weight increase or decrease the strength of the signal at a connection. Then we have bias. Sometimes a bias term is added to the total weighted sum of input to serve as a threshold to shift the activation function. Then we have the output layer. The function of the output layer is just like hidden layers. The outputs are passed on to the world outside of the neural network that we have made, and output layers simply give us the prediction, for example, for classification. So here we continue studying the architecture of artificial neural networks. So you can see here 3 networks with different layers, right? Number of input unit is dimension or dimension of features, right? How many features we have, they will be the input layer. Then the number of output layer is the number of classes. For example, for spam detection, we may have 1, right? So by default, we may try only 1 hidden layer. But if we have more than 1 hidden layer, we may have the same number of hidden layer units in every layer. Usually, the more, the better. We may try some grid search, that is a model hyperparameter optimization technique. More hidden units equal to more capacity. The same number of units per hidden layer is also good default. We often use grid search to find the best setup. So what is grid search? Grid search works by exhaustively evaluating a model for every possible combination of a predefined set of hyperparameter values. The next one is activation function. The activation function is arguably the most important nonlinear component of artificial neural networks. If we didn't use an activation function, or if we use a linear one, the network, no matter how many layers it had, would just be computing a single complex linear equation. It would never be able to solve complex and nonlinear problems. The activation function serves 2 crucial purposes. One, introduces nonlinearity and squashes the output. This activation function allows the network to learn and model complex and curved decision boundaries. And also, it keeps the output of the neuron with a manageable range, like 0 to 1 or -1 to 1. And in this way, it prevents values from exploding to infinity during training. Activation function transforms neurons input into output. So we may have different kind of activation function like sigmoid, ReLU, leaky ReLU, TNH, ELU, etc. The first one that we're going to study is sigmoid activation function. Sigmoid was one of the earliest and most popular choice for activation functions, particularly in the output layer for binary classification. The formula that you can see here, gz is equal to 1 by 1 plus e in power of minus z. As you can see here, it ranges from 0 to 1, and it's not 0 center, so the center is here. And it have exponential operations. It squashes the input value into a range from 0 to 1, and in this way is an excellent choice for representing probabilities. What is the problem with this sigmoid function? The problem is vanishing gradient. Its derivative is very small for large positive or large negative input values. When the gradient is near 0, the weights stop updating effectively, and this problem we call it as vanishing gradient problem, right? So when the gradient is near zero, the weights do not update effectively. This problem is called as vanishing gradient problem. That's why sigmoid is rarely used in hidden layers for deep networks. The next one is tangent edge or hyperbolic tangent. It's a closely related and generally superior alternative to the sigmoid function. The formula is here: fx is equal to e in power of x minus e in power of minus x, e power of x plus e in power of minus x. As you can see, it ranges from -1 to 1, and it is zero center, and also it has the problem of vanishing gradient problem. Like sigmoid, it has a S shape that you can see here, but it maps the input from -1 to 1 because the zero center output helps in centering the data for the next layer, which can make the optimization process more stable. What is the problem of this one? As I said, vanishing gradient problem. It's still suffer from vanishing gradient problem at the extreme ends of the input range, but it is less severe compared to the sigmoid. The next one is ReLU. ReLU stands for Rectified Linear Unit. ReLU is considered as the default choice for hidden layers in modern deep learning models. It is elegantly simple and it is very effective. The formula is very simple. Fx is equal to max of 0 and x. So we can see here, if it is less than 0, 0. If it is greater than 0, x, as it is. So the range is from 0 to plus infinity. It is computationally efficient and it is critically avoid the vanishing gradient problem in the positive region. This allows deep networks to learn much faster. So what is the problem of ReLU? If a large gradient pushes a neuron's weight such that its output is always negative, its gradient will be zero forever. And then the neuron effectively dies. It means what? It means it stops learning. Then in order to solve this problem, leaky ReLU has been introduced to solve this problem. So in the case of comparison, sigmoid is slow and saturated. Tangent is better but still saturates, but ReLU is fast and powerful. Leaky ReLU does not have the problem of the ReLU. In neural networks, we have input layer, we have one or more hidden layers, and we have an output layer. Input, we have some xi's. For every I, we have input example like x1, x2 up to xn as the number of features we have. Then we have some hidden layers. We may have one hidden layer, two hidden layer, or more hidden layers. And accordingly, we calculate the value of each neuron based on the values coming from the previous layer as well as weights and bias. So we apply sigmoid function in order to select which neurons values should have impact on the value of the next layer neuron. Then we have some output layer, as you can see here, for example, for classification, right? And finally, based on the result, we will calculate error using the loss function. Loss function is simply the difference between predicted and actual. It will tell us how good our model predicts. So in summary, we have input, we have weighted sum, activation function, next layer, then loss. So this is, once we go up to here, we call it as feed forward. We calculate the loss, we come back, and we call it as backpropagation. We will study it later. Inputs are flexible. Input can be, for example, any real value. Also, it should be noted that the input values are highly correlated or independent. Target function may be discrete valued, real valued, or even vector of discrete or real values. Outputs are real numbers between 0 and 1. Artificial neural networks are normally resistant to errors in the training data. That's why they are used a lot. We can see some disadvantage of artificial neural network, that is long training time. It takes a long time, but artificial neural network, we have some fast evaluation also. And finally, we should know that the function produced using artificial neural network can be difficult for human being to interpret. We're going to study the learning procedure in artificial neural networks. So learning is the method of modifying the weights of connection between the neurons. And our goal is to find weights and biases that minimizes the cost function. This is our ultimate goal. In here, we can try supervised learning, unsupervised learning, and reinforcement learning for learning procedure in artificial neural networks. In here, in the case of supervised learning, the model learns value of weights from input-output pairs. Artificial neural network start with random weights. Then we load training examples as input. So then the model try to do prediction or generate the output, right? Then in order to improve the model modify weights in order to reduce the difference between the actual output and predicted. Right? So this difference must be minimized. We try to modify weights in order to reduce this difference. Again, the same procedure is iterated over all training examples. Finally, we terminate when weights stop changing or when the error is very small. Then the next one is unsupervised learning. In here, we try to form cluster of patterns according to their similarity. Then when a new input pattern is applied, the network assigns it to a cluster that input pattern is similar to. In this type, we don't have any feedback from the environment. The network must discover the patterns. And then we have reinforcement learning. There is some feedback from the environment. The feedback is evaluative, which means there is no teacher as in supervised learning. After receiving the feedback, the network perform adjustment of the weights to get better predict information in future. So let's look at the history of artificial neural network. The history of artificial neural network is marked by periods of great optimism known as AI summer, and also period of reduced funding that is called as AI winter. The journey began in 1943, where here McCullen and Pitts, who they introduced first computational model of a neuron. Then in 1957, the perceptron was introduced. It was the first working single-layer neural network that was capable of supervised learning, but it could only solve linearly separable problems. The breakthrough came in 1986 with the popularization of backpropagation algorithm. Backpropagation algorithm finally allowed us to efficiently train multi-layer networks, resolving the perceptron limitation and also initiating the second AI summer. Finally, the era of deep learning began in 2006, largely driven by better hardware like GPUs and massive datasets. And in this way, the artificial neural network was enabled with thousands of hidden layers, and this led to incredible AI advancement, what we see today. So what are the applications of artificial neural networks, or when we should deploy a neural network? Artificial neural network excel at problems where the relationship between the input and output is highly nonlinear and complex, and also difficult to model using traditional statistical methods. Some prime applications like classification, signal processing, pattern recognition, time series prediction, control system, and many more. In the case of classification, we try to recognize image, detecting, for example, spam, or identifying fraud transactions. Or in the case of like pattern recognition, finding trends in large noisy data sets such as medical data. Or in the case of like time series prediction, for example, forecasting stock price or weather. Or we can use it for control systems like for robotics and autonomous vehicles. Essentially, if you have a lot of data and you have a complex problem where human intuition struggles to define the exact rules, we can use artificial neural network. So let's closely look at the different components of artificial neural networks. Artificial neural networks are made of artificial neurons in different layers, right? So here we have input layer. This is the features or the neurons in the input layer. Then we have one hidden layer here, and we have one output layer here, right? So if we have a single hidden layer, we call it as shallow neural networks. If we have more than one, then we call it as deep learning or deep neural networks. This X0 that you can see here, it's a bias for input layer, and this one is bias for the hidden layer, right? So these are different layers of artificial neural networks. So we have a feed forward or forward propagation algorithm, and we have back propagation algorithm. The process of calculating the network's output is called as forward propagation. It's the mechanism the network uses to make a prediction. The steps are sequential. We move from the input layer and we will end it at the output layer. So we have some data like X, and this X is fed into the input layer as the layer number 1. Then for every neuron in the next layer, we calculate the weighted sum of output from the previous layer. Then we can show it by, for example, AL. And also we add bias, as I said here. We have bias for different layers. Then we pass this network input through the activation function, and we get the output of the current layer. This output becomes the input for the next layer, and the process repeats until we reach the final output layer, which is the network prediction. So we have neurons in each layer, and they are connected using some channels. Each channel is assigned a numerical value that is called as weight. The input is multiplied by its corresponding weight. Then we take some of them and we will pass them to the neurons in the next layer, like we call them as hidden layer. Each neuron may associate it with a numerical value that is biased, right? And then we will pass them through the activation function. The activation function decides that whether a neuron will be activated or not. Then if a neuron is activated, it will transmit data to the next layer over the channel that we have already. And finally, in the output layer, the neuron with the highest value will determine the output. So once we did the forward propagation, we calculate the loss, and then we apply back propagation algorithm. If the loss value is not acceptable, it means we need to train the network. For example, we compare the predicted value with the actual value in the test set, or we can say validation set. Then we will find out with some value that is error, right? So the loss or the error, it means that magnitude of the error. It's simply the difference between the actual and the predicted value. Such information about the error is sent back, that we call it as back propagation algorithm. Then hyperparameters like what? Like weights are adjusted based on the received information. Then again, we will do forward propagation. Again, we calculate the loss, and if it is needed, we apply back propagation. So forward, backward, forward, backward. Iteratively, we perform them until convergence. How long it may take time, seconds, minutes, hours, or days. So in modern application, we use vectorized computation for efficiency. Let's look at the mathematical notation for a single layer. So as I said, this is the input layer, this is the hidden layer, and this is the output layer. And x0 and a0 here, they are the bias. So we have aij, this is the activation of unit I in layer j, and theta j is a matrix of weight that control function mapping from layer j to layer j plus 1. So we want to see what is the value for these neurons. The value for this neuron is simply g. G is the sigmoid function, and the value is theta 101. Theta 101, it means mapping from layer j to layer j plus 1, right? Multiply x0. So it means the weight of this channel multiply value of this one. Then, so let me clear this one. So it will be, this is the sigmoid function, and we want to calculate the value for this one. It will be x0 multiply the weight of this channel, right? Then it will be x1 multiply the weight of this one, plus x2 multiply weight of this channel, plus x3 and weight of this channel, right? So one value from here and weight of each channel, then we will pass through a sigmoid function. The same we will do for a2 and 2. So this is the sigmoid function, and here again x0 and weight to x2, then x1 and weight to x2, this one, x2 and this one, and x3 and the weight for this channel. Then we will do the same for this one, x0 and weight, x1 and weight, x2 and weight, and x3 and weight. Finally we can have this one, right? Then for the value of this one as this value of these neurons, we will do the same. A02 multiply weight of this channel, right? This A12 weight of this channel, A22 weight of this channel, and value of this one multiply weight of this one. It will give us the output. So let's consider all these values as z12, right? So as z, this one as z, this one as z, and this one as z, right? So you can see here, we write a12 as g of z12. So we consider all these values as z12. This one as z22, this one as z32, and this one as z3, right? So we can write in this way. So a12 is g is a sigmoid function, right? Activation function, z12, z22, z32, and finally this is z3, right? So this is the output. So x is values from x0, 1, 2, x1, x2, and x3, and z2 is z12, z22, and z32. So from the previous slide, we found the pre-activation vector, and we applied sigmoid to the value in each node. We consider also bias. So let's do it here. We find that a12 is g of z12 in here, right? In here, we already found these things in here. Now, so z2 here is equal to theta 1 x, right? It means theta 1 a1, and a2 is equal to sigmoid of z2, this value that we found here. Then also we add a bias here, and z3 will be equal to theta 2 multiply a2, and finally we can find out the hypothesis as h theta x is equal to a3, which is equal to sigmoid of z3 based on calculation in the previous slide. Here you can see one deep neural networks because we have here more than one hidden layer. So this is layer number 1 or input layer, this is layer number 4 or output layer, and in between we have two hidden layers, right? Two hidden layers. And if an artificial neural network have two or more hidden layers, then we call it as deep neural network, or simply we call it as deep learning. Normally, based on the empirical results, the deeper network generalize better, but not always. It can be improved to some level. So the number of hidden layers affect the classification accuracy. Question is, how many hidden layers we must have? Is it okay to have too many hidden layers? No. Based on this graph that you can see here, if you have 3 hidden layers, maybe the accuracy is here. If you have 4, it is 93%. If you have 5, it is 95. If you have 6, 95.5. But you can see here, after some time, the growth becomes same. It means having 11 hidden layers and 20 hidden layers and 30 hidden layers is the same. So the best case is to have 11 hidden layers, right? It doesn't mean that deeper network always is the best, right? So we have to find out the efficient number of hidden layers. For more complex network, there is no rule to decide the number of hidden layers. It's very simple. We just keep adding layers until the test error does not improve anymore based on this graph that we have seen here. So in here, you can see if we consider NH as the number of hidden layers, and if NS is the number of samples in training data set, and if alpha is number of non-zero weight for each neuron, if NI is the number of input neurons, and NO is the number of output unit neurons, then we can decide the number of hidden layers based on this one. We have also cross-validation. Cross-validation is one solution for overfitting. It means once we identify the best combination of parameters, we test the performance of that set of parameters in different contexts. And for that one, we can use different kind of libraries like cross-regressor or grid search CV. Artificial neural networks come in many shapes, but they are broadly categorized based on their connectivity patterns. We have like feed-forward neural network. This is the most basic and common type. We use this one for classification and regression. Information flows only in one direction, from the input to the output. We may also have recurrent neural networks. These networks have feedback loops in their connections, and they allow information to cycle back. This gives the network memory, and it makes them ideal for sequential data like text, audio, and time series. We have like convolutional neural network that is specialized for grid-like data, for example, for images. And recently we have transformer network. These transformer networks are specialized for sequence-to-sequence tasks and currently dominate the field in natural language processing. So this ChatGPT, Gemini, and other friends, they use transformers, and also they use vision transformer for image. So you can see here different models of artificial neural network like perceptron feed-forward, RBF, deep feed-forward, recurrent neural network, LSTM, GRU, autoencoder, variational autoencoder, the noisy autoencoder, sparse autoencoders, Markov chain, Hopfield network, Boltzmann machine, restricted Boltzmann machine, deep leaf networks, and many others that you can see here. So far, we only consider one output, right? So we say binary. If it is 1, it will be a spam, for example. If it is 0, it is not a spam. But in many cases, it's not that much easy. For example, when a car is driving in a street, they can see too many objects. So we have to do multi-class classification when we have different classes as output. For example, here we have 1 output, 2 output, 3 output, and 4 outputs, right? So if we have a set of images and we want to categorize them, whether there is a pedestrian, car, motorcycle, or truck. For this problem, we need to go for 1 vs all algorithm. So in here, what we do, we have to do it in 4 different ways. In the first time, we consider pedestrian as 1 and the rest as 0. Next time, we consider the second one as 1 for car and the rest as 0. Next time, we consider the third one as 1 and the rest as 0 when it is motorcycle. And for the other case, is when there is a truck, right? So for multi-class classification, we have this network. These are the input, and these are the hidden layers, and these are the outputs, right? So we can have a training state like x1, y1, x2, y2 up to this one. And for pedestrian, we consider this one as 1, the rest as 0. For car, the second one, third one, and fourth one here. So for the binary classification, we have y as 0 or 1. But in here, in multi-class classification, we have k classes. That's why y is r of k. So you can see here, this is a 4-dimensional vector. In here, we have 1 output unit, but in here, we have k output units, right? K output units. In here, h theta x is in r, but in here, h theta x is in r k. SL, the number of output is 1, but in here is k. K is equal to 1, but k here is more than 3. So as we already learned, we have cost function. The cost function is simply used to calculate the error of the prediction. If the error is not acceptable, then we have to apply backpropagation in order to change the hyperparameters, and then we have an acceptable output. So in here, we have this j theta as the cost function, and this is for multi-class classification. It has 2 parts. One part is here, and the second part is here. This is simply called as a cross entropy loss term, and this is for regularization term. So we have yki here. This is for k classes, right? It is multi-class classification. M here is the total number of training, and K is the number of output classes for the classification. Xi here is the ith training input or example that we can think of. And this Yki, as I said, this is the actual label for the class K of the ith example. Then in here, we have theta xik here that we find the log of it. This is the predicted output probability for class K of the ith example. This cross entropy measures the dissimilarity between the true probability distribution that we show by y and also the predicted probability that we show by h theta xi. Then in this part, we have regularization. This is the penalty applied to magnitude of the network's weight. So this is called as L2 regularization. So in this case, lambda that you can see here, this is the regularization parameter. It controls the trade-off between minimizing the training error and keeping the weight small. Then we have L here. L is the total number of layers, and this small l is the index for the current layer. And this SL that we have here, this is the number of nodes in layer L. And this theta JL, this is the weight connecting the ith unit in the layer L to the jth unit in the layer L plus 1. Our goal here is to minimize the cost function, right? Minimize the cost function, and we can use gradient descent, partial derivative of the cost function with respect to theta. So now we want to see what to do in backpropagation. Backpropagation is a method to update weights in neural networks. How? By taking into account the actual output and the desired output. The derivative with respect to each weight, like W, is computed using the chain rule. Using forward propagation, we found the error. Now we go back and apply backpropagation. So we have to calculate error at each node. So in here, we show like delta JL. Delta JL is the error of node J in layer L. For example, delta JL is the h theta x for the predicted value, right? This is for the predicted value. So we calculate in this way. We try to find out the error based on the activation of the unit. This is the activation of the unit, and this is the actual value in the training set. So you can say this is predicted and this is actual, right? So in the same way, we do for other layers as well. So we go back from this side, from 4 to 1, from 4 to 2, right? 1 is input layer. From layer 4 to layer 3 to layer 2. So this is for layer 3, and this is for layer 2. The current error has some effect of the error of the previous one. So error at layer 3 affected by error of layer 4. Layer 2 is affected by layer 3. So then we have g prime z3 here. This is the derivative of activation function that can be written as al multiply 1 minus al, right? So in this way, we can do it. Finally, we try to find the partial derivative of j theta as the cost function with respect to this one, which is equal to this one, right? So we apply backpropagation to adjust the hyperparameters. So here is the backpropagation algorithm. We have a training set like x1 by 1, x2 y2 up to xm by m. In here, we try to find delta. Delta is used to calculate what? To calculate partial derivative of j theta as the cost function with respect to j theta I j l, right? Initially, we consider this delta as 0. Then from from 1 to n, we do so set a1 as xi. Xi is the input, right? Then we apply forward propagation to find out AL for layers 2, 3 up to L. Then using YI, we compute the error, right? Predicted minus actual. Then we find the errors in different layers, up to layer number 2. Layer number 1 is not included. Then we try to update it, right? So delta IJL is equal to, this is update, delta IJL plus AJL multiply delta JL plus 1. So then in order to find the rate, if j is equal to 0, then dijl is equal to 1 by m delta ijl plus lambda into theta ijl. And if j is equal to 0, then we go in this format and we will find the derivative of our function. This one should be here. So what problems are good for artificial neural network? When we have input with high dimension and they are discrete or real valued. When output is discrete or it is real valued. When output is vector of values. When we have noisy data. When we have long training time is okay, no problem. When we have fast evaluation of learn function required. And when it's not important for human to understand the weight. Okay, so to wrap up, neural networks learn features automatically. They are highly nonlinear, they are parallel, and they are very, very powerful. Backpropagation is just reverse mode automatic differentiation. This is a math magic. We use them when data is in very high dimensional, when we have a complex problem, and when we can accept long training process, but we want to fast inference. This was just an introduction to artificial neural networks. Please practice and code them, and feel free to ask me if you have any questions.